Welcome to Lecture 11B, continuation from Lecture 11A on triple integrals, but here we'll focus on some techniques and examples. Again, this material will be from reading assignment 3, and the objectives are similar to what we outlined in Lecture 11A. Here, though, the concepts we'll be looking at are a decomposition technique, which is used if basically you have a volume for which you are not able to set things up with 6 bounding surfaces. So the question is, how do you deal with that problem? And also, again, a little bit more on how to visualize an enclosed volume. And again, a reminder, it's important that you learn how to sketch a region, since this will assist you in determining the bounds on the integral. All right, again, the second slide is just a summary of the contents of this lecture. You'll notice I've taken a couple of examples from the textbook, which are more tricky ones, and I've illustrated them in this particular lecture. Okay, so the next item to consider is the decomposition into subdomains. We discussed this to some extent when we dealt with double integrals, but now when we're dealing with volumes, the bounding entity is a surface rather than a contour. So if we're dealing with complex object, then the domain of interest must be divided into subdomains if at least one of the following conditions exists. One or more surface bounds on the inner or middle integrals is defined over its range by 2 different functions. We call this multi-valued. Second possibly is one or more of the surface bounds on the inner or middle integrals is not continuously differentiable. And thirdly, one or more of the surface bounds on the inner or middle integral is not one-to-one. So let's look at the 2 examples here. So this is basically an example of non-differentiability. So if you were to follow the bounding surface here, basically it's flat up to this point, and then suddenly the orientation changes. So this point, basically, at this point, there's no differentiability when you go in this direction. Going along this direction, of course, there's no issue. Now, if this were a function which was smooth and then differentiable, but then a different function on this case, we'd still end up with the same problem. Namely, we have to break this up into 2 separate subregions, this region and this region. Notice in this region, you have one continuous surface for the upper bound, and one continuous surface for the lower bound. Similarly on this one. So essentially integrating over this region in this and integrating over this region and putting the 2 together is like integrating over the whole region. If you want to look at this case and the one on the left, then you can go to this link and basically try to visualize what's happening. Now this is an example of a not one-to-one. And so here the issue becomes one of determining when you basically draw a plane, slice through the object. What you want to make sure is that the upper bound basic you're dealing with is one-to-one. In other words, for any given slice, you essentially have only one contour that you see on the surface. Similar to the case when we had 2D, where we basically took a line, and if the line intersected at 2 different points, then it wasn't one-to-one. So for example, here, one could essentially say that this upper hemisphere would be an upper bound, and then this lower plane, which you can't see here, would be a lower bound. So this would basically could be integrated with a single integral. On the bottom side, similarly, if it was the bottom hemisphere, the bluish tint that you see here would be the upper bound on the surface, and this hemispherical bowl would be the lower bound. Now the middle region that you see here, yellow, again, from here it's difficult to see, but you would run into a problem here because this has got a slanted slope on this side and on this side. So effectively, it looks more like a cylinder which is sort of slanted. In this case, we would have to break this up into another region, which would be one in which this basically would be a pure cylinder up to this point. And this would be some form of sort of a triangle, but sort of extruded around in a circle. And so there'd be one region that would be essentially the region which is this slight sliver that goes around, a cylindrical region, this top dome, and this lower dome. So in effect, 5 different regions would be required in a case like this. If these were just 2 straight lines going up and down, then there'd be no issue, because then it would be 3 regions, red, blue, and yellow. Right? In this case, in the middle case, you would have an upper surface, which is a plane, and a lower surface that's also a plane. And the exterior surface would just be the surface of a cylinder. Anyways, you can look at this in more detail if you click on this link here. So effectively, if we have two regions like this, and you break it into subdomains, then you'd be integrating over one domain and adding it to the integral over the second domain, and this is equivalent to basically the integral over the full domain. All right, so one question that quite often comes up is how to visualize volumes of integration. So for example, swapping dz dxy for dx dzy for an arbitrary volume requires a pretty good sense of the volume of whatever it is being integrated and its traces projections on the coordinates planes. And so these are sort of questions that have come up in the past, but related to acquiring a sense of the volume when presented with non-obvious functions, i.e. not a box-like structure. So one question that came up quite often was, should I memorize equations for various surfaces, graph things on Math3D or whatever program you want to use until I get an intuitive sense of it, or is there some other method? And the answer essentially is always the same: graph whenever possible. Perspective diagrams and projected regions are very useful. There's no need to put everything on one graph. For example, graph upper and lower surface, obtain bounds on the integral, and then graph the projected region to determine the bounds on the middle and outer integral. So the projection effectively gives you the region over which the integration takes place, which would be essentially the outer integral and the middle integral. Second question that often came up is it a matter of some three higher dimensional spatial sense reasoning? Example, looking at a function, knowing intuitively what it looks like in 3D. The answer is simple. It's just that the bounds you have to visualize are as being just plain surfaces. Sketch each of the 6 surfaces, and everything enclosed by all 6 surfaces is the domain. Third question that has come up quite often is it a matter of pattern recognition? Example, looking at some function and knowing via recognition that is a hyperboloid of one sheet and memorizing the traces. The answer to this is, well, we typically have simple surfaces, quadratic surface, hyperboloids, ellipsoids, spheres, paraboloids, things of that nature. So the first thing is to try to understand each surface that you'll integrate. So for example, the surface z equals square root of 9 plus x squared plus y squared is 1/2 of a hyperboloid. And z equals 9 plus x squared y squared is a paraboloid. Z equals square root of 9 minus x squared minus y squared is a hemisphere. And z equals c times the square root of this argument with coefficients a and b is 1/2 of an ellipsoid. Note, the other half of the hyperboloid, sphere, and ellipsoid is obtained by changing the sign of the square root. So this is for positive z. Put a minus here and it gives you the other hyperboloid sheet. Putting a minus here gives you the hemisphere, which is below the z equals 0 plane. And lastly, is there some analytical method for determining the shape? Do I just graph the traces manually and try to figure it out from there? General word of guidance is it might be easier in the beginning to sketch out each of the 6 surfaces independently and then do a composite sketch. Later, you can do it all on the same graph as you get the necessary experience of graphing and sort of visualizing what's happening. All right, so let's look at some of the questions in the book. And this is question 25 from chapter 16.4. A question asks you to compute the volume of the wedge of the cylinder, x squared plus 4z squared equals 4, created by the planes y equals 3 minus x and y equals x minus 3. So I basically have chosen to look at this problem in 3 different ways, and you always will pick the one that's the easiest to solve or the one that you're most familiar with. So option 1A is to work directly with the object. Option 1B is to break it up into regions. That is not necessary. I've just shown that it can be done, and would be the case if you really had to do a decomposition process. And option C is to turn the object basically right side up. So that means y is pointing upwards rather than pointing to the right. Okay, so how do I know, for instance, that the picture as given on the left is in fact the correct picture? Well, if you look at the first equation, x squared plus 4z equals 4, y is not indicated. So what is that actually? That's basically the equation of an ellipse extruded in the y direction. So that's more or less the blue part of the object that you see, which is this surface here that wraps around the back side. All right, and then the plane y equals 3 minus x, and planes y minus 3x, and y equals x minus 3. Well, this plane that you see here, all right, this plane in this slightly orange surface here is going to be y is equal to 3 minus x, whereas this plane that you see here, which just slices through the cylinder here, this would be x minus 3, y equals x minus 3. By the way, if you want to look at this in more detail, you can just click on this interactive URL here, and you'll be able to play with this a little bit if you wish. All right, so now let's set up the integral. Now, if you look at this, basically, this equation can be written out as z is a function of x, and there'll be two parts to it, the positive and the negative root, which mean an upper and a lower surface, and we're going to choose to do an integration with z followed by y followed by x. It just works out. That makes sense to do it that way, and I'll just explain in a minute. All right, and then you have y equals 3 minus x and y equals x minus 3. And so effectively, let's start by looking at doing this directly. All right, so if we do dz first, then z as a function x would be this as an upper surface and this is a lower surface. So the next question would be, should I do dx or dy? Well, the next one should be such that basically does not include z, because z's already taken care of. So if we do y, then y must only be a function of x. Well, it turns out that's correct, because y is 3 minus x and y equals x minus 3. This will be the lower bound, because essentially it's a smaller value of y, and this will be the upper bound because it's a larger value of y. So with respect to y, this is more positive, and this surface is more negative. And then the range of x is determined basically by the domain here. So the x values here can go basically from -2 to +2. Otherwise, the square root has no meaning. So that's essentially the integral. Now, if I broke that up into regions, that means the only thing that would be impacted would be the middle integral, because I'd be talking about slicing basically at different values of y. So here, for instance, I could slice right at this point where these two form a nick. So one is here and another one here. So that shows you the blue region, the center, and the outside on the right. So this nick would be occurring at a value of -1, and this nick will be of y minus 1. This will be y of +1. The left and right surface don't change. So you can see here is x minus 3 on this side, and here's 3 minus x on this side. So these are color-coded. That goes with that, that goes with that, that goes with that. And if you do this calculation, you'll get 12 pi. All right, let's basically look at another option, and that's to turn it sideways. All right, so in this case, I've got it y on the top. Okay, x is in this direction and z is in this direction. Now, be careful. Remember that when you start turning things around, you've got to keep the labels on the axis. Why? Because we have to maintain a right-handed coordinate convention. So that means z is actually pointing in this direction and x is in this direction. So we can solve this problem, which is what I'll be doing on the next page. Now z basically is bounded, y is bounded on the top and the bottom by these two planes. All right, so I've got an interactive module here you can look at. I mean, the two upper surfaces are in red. The side surfaces, that's the middle integral, are yellow and basically separated by these two black lines. So one surface would be basically z equals 4x squared. Z is here, x is here. So this would be along in this plane here, z is x. So that would be one surface is here, one surface would be here, front and back. Okay, top is 3 minus x, bottom is x minus 3. Then we're doing x. And so that would be now, we turn the equation the other way around and solve in terms of x rather than z. This will be -2 square root 1 minus z lower bound, 2 square root 1 minus z upper bound. The domain of this function is between -1 and +1, so the integration bounds on the outer integral are between -1 and +1. Okay, this is the original. Or you could also do it the other way around. If you do, instead of dy dx dz, you do dy dz dx. You could do it this way as well. Then, of course, now this is z as a function of x, and you can see this is similar to what we'd seen earlier. But now the domain of x is going to be between -2 and +2. That's where the square root takes on values which are real. So you see that. So either this approach or this approach essentially will still give you the same answer. That's 12 pi. So in this case, you can see that there were two different ways to solve this problem. Again, we iterated the integral, but the main point to remember is that if you have, say, y, x, z here, then this can only be a function of x, z. This can only be a function of z, and this can be only a function of x. Similarly here, if you have dy dz x, this can be a function of x and z. This can be a function only of x, which it is, and the last one basically would be just between two constant values, upper and lower bound. All right, let's look at another example, question 69 from the same chapter. Find the equation for the bounding surfaces, set up a volume integral, and evaluate the integral to obtain a volume formula. So it's a spherical cap with a radius r and a height h. All right, so this height is h, and essentially what we're interested in is only the volume within this region here, and the radius of the sphere is r. So in this case, basically, we need to set up the inner, middle, and outer integrals. And so we're going to use z as the integral. And so the top surface would be this one here. It's just the equation of a sphere. So you can basically write that as z is the square root of r squared minus x squared minus y squared. On the lower portion here, this is a plane. The plane is at a certain value z. Well, this distance is r. If this distance is h, then this distance, which is height of z, would be equal to r minus h. So that's this. So there's the upper surface, there's the lower surface. Right, what about the middle integral? Again, these are going to be surfaces as well. So in this case, basically, you need to figure out the intersection line, which is going to then be projected on the xy plane, which means you take the equation of the sphere and the equation of the plane and equate them, which is what I've done here, and solve for y. And if I solve for y, I end up with a square root of this expression, plus or minus. One of these will be the upper surface, and the other will be the lower surface. Again, z is not mentioned here, so z is basically extruded into positive and negative directions. So in fact, it's a cylinder, or two semi-cylinders, half cylinders. So in this case, the right surface will be the larger value of y, and the left surface will be the lower value, which is a negative value. And then for the outer integral, we'd be basically looking what is the domain of this, right? And the domain of this is where this basically remains a real number. And so that's solving for x, and turns out x will basically range between a positive square root, which is the larger of the two, which means it's the front surface, and the smaller two, which is the negative of the square root. So by doing this, we immediately have set up the bounds for the integral, right? And the ordering is also clear that this order will be dz, right? The second will be dy, and the last will be dx. If you look at this in terms of a picture, then more or less this is what we're dealing with, right? We've got basically x is basically two planes, okay? And we have basically that the surfaces would be upper sphere and would be a plane, as shown here. The sphere is basically recognizable. It's actually just buried inside there if you want. So there's an upper surface there, a lower surface there. The middle integral is basically this surface here and this surface here. And the outer integral is between these two plates here. All right, so then we basically just go through the calculation process. Here I've just transferred the information from the previous page. This is the limits on the z, this is the limits on y, and the limits on x. All right, and so if you do this integral, basically would mean you just dz is z, so it'll be this minus this. Okay, that's all you end up with for the integral of that. And then the middle integral is nasty, okay? And so you end up with this. And you can do it if you want, but the exercise is not going to be knowing how to do integrals of this sort. I will either give you a formula to tell you this has a certain form, or I'll just ask you to set up the bounds. So I don't expect anything of this sophistication. And as I mentioned down here, if you really want to know how to do integrals of this form, this tool that offered by Wolfram is useful because it'll actually give you the integrals for anything you put in there, as long as it's something for which they have a library. All right, and the outer integral basically would be taking this now and integrating with respect to dx between the limits on x, and you end up with this as an expression. Note, this is a difficult integral to solve. Solving it in Cartesian coordinates is not a good choice. Later we will see that it's more convenient to solve this problem in either cylindrical or spherical coordinates. All right, so this is another example. This is from question 21 in the chapter 16.4. You're supposed to compute the volume between the sphere x squared plus y squared plus z squared equals 19 and the hyperboloid z squared minus y squared minus x squared equals 1 for z greater than 0. And so how do we set this up? Well, I think more or less from the previous example you can see the procedure. So I've just basically made a couple of statements in note 1. The bounds, so the upper surface is clear. You just have to determine what z is. And so that's this. And the lower surface is the hyperboloid. So you determine what z is in this case. So those are taken care of. These two basically, though, the bounds in the middle integral are found by equating the upper and lower bounds of the inner integral, which is these two. Equate these two and solving for y. Then you'll end up with these two expressions. One would be square root positive 9 minus x, square root negative 9 minus x squared. So this is the higher of the two, so it's on the top. This is the lower of the two, so it's on the bottom. And the domain of this is between 3 and minus 3 and 3, so that's why this is the lower bound and this is the upper bound. So the answer is provided here, but again, I didn't solve it. It's quite a laborious procedure, but we'll find that this is much easier to solve either in cylindrical or spherical coordinates. If you want to look at basically the surfaces here, that's the outer integral, which are two planar surfaces. The the middle integral, basically where these two sort of semicircles, divided basically by these black lines. And the upper surface on the innermost integral is this, and the lower surface is the one you can barely see here at the bottom. Okay, so let me look then now at the last particular example. This is also one which is a bit tricky. So this problem statement is one sphere is centered at the origin and has radius r. Another sphere is centered at 0, 0, r and has a radius of r, where r is greater than capital R over 2. What is the volume of the region common to the two spheres? Now, you may find it convenient to draw XZ trace to assist you in visualizing the object. I have set up the simulation so you can see it for yourself. So the top surface basically is a sphere. So the equation of a sphere is x squared plus y squared plus z squared equals r squared. But we want to express it in terms of z. So the top surface will be the positive square root, which would be r squared minus x squared minus y squared square root. The bottom surface would be just a sphere which is being displaced by r units in the z direction and has a radius of little r. So this is its equation. Or if you simplify it, you end up with this. And we want this in terms of z, so you end up with a quadratic equation in z, and you can solve for z. And this is the root that basically refers to the lower portion, the bottom surface. So that's what you end up with. Again, these are basically the top and bottom surface are in red. The yellow represents the middle integral, which is the right and left surface. The black lines separate the two regions. And the blue are the front and back surface, which represent the outer integral. All right, so in Cartesian coordinates, the bounds on y, we know what the bounds on z are, but on the y are termed by taking the equations for z for the two surfaces and equating them and solving for y. So I've equated these two, solved for y, and up with this expression here. If I wanted the domain of x, which is the outermost integral, then I'm looking at under conditions, does the argument of the square root remain real, which is between a lower and upper limit of x. And if you solve this for the case where this is equal to 0, you'll end up with two solutions for x, this being one of them, and this being one of them, and this being the other one of them. And so now we have basically expression for y, which is this one, upper and lower limits, expression on x, upper and lower limits, z already given on the previous page, so we can set up the integral. So there's z upper surface, z lower surface, y upper surface, y lower surface, x upper surface, x lower surface. You can do this integral and you'll end up with this answer, but this is a mess, okay? And we'll show again that this is an easier problem to solve if you're dealing with either cylindrical coordinates or spherical coordinates. So that basically concludes lecture 11B. Thank you for listening.